Dear students, I am going to discuss the topic called deterministic finite automata. In the previous class, we have seen some introduction. There we have seen some how the finite automata can be classified either more and Mealy machine or finite automata and deterministic finite automata and epsilon finite automata based on the output. We have seen that, right? So continuation of that today. Now we are going to discuss the topic called deterministic finite automata and conversion of regular expression to deterministic finite automata and the epsilon NFA and NFA or non-deterministic finite automata. Right. So coming to the introduction, after introduction, let we see that how can construct the deterministic finite automata, the architecture of the deterministic finite automata. It basically comprises the 5 tuples, that is 5 attributes. So the first attributes you can see that Q is a set of states, right? So for example, Q1, Q2, Q3, which are the states in the state diagram, right? The state diagram is for any string or language we want to accept by the machine. Then the number of states is essential. So those are the finite number of states is essential. That is example called Q1, Q2, Q3, so on. The next one is the second tuple or second attribute of this deterministic finite automata is the sigma. Sigma is the number of alphabets. It's a combination of maybe numbers and numerals and alphabets may be there. So there is it is called an inputs. How many inputs are there in a state? For example, sigma is equal to a comma b, right? So there is 2 inputs may be considered. Those are a and b. Similarly, there may be a number, so on, that is. So the third tuple is a combining of this sigma and q, that is a state q into sigma, that is a Cartesian product, right? Delta is a transition function. So delta we can obtain by that q into sigma, that is how many number of transition may be possible up to q, right? Up to q is the transition function. So the third attribute or the fourth attribute, that is one example of transition, that delta of current state comma input. So at the current state we are pushing some input, then what is the next state? Next state may be same current state or new state may be possible. So that is an example of transition. So further example of that transition, we can have that example delta q1, delta of q1 comma a is a input, right? Q1 is a current state, right? So then q2 is a next state, right? So this is a transition, one transition. So delta of q1 comma a is equal to q2, set of q2. So q2 could be the next state or current state possibility. So the fourth attribute is a q0. Q0 belongs to q, is the start state, right? So with help of the single circle, they will represent that is. So coming to the last state or last tuple, that is a finite the final state or accepting state. So accepting state, that is a f is a subset of the q, proper subset of the q is a set of the accept state, right? So which is represented with help of the double circle, right? So these are the 5 major tuples going to be employs to the construct the deterministic finite automata. So then we can have that the L, that is a language with a machine M, right? Language of machine M. So language of machine M, the set of all strings machine M accepts, right? So a set of all strings will be that machine will be accept. So that language of the machine, we can call it as, right? So having understood these 5 tuples of the deterministic finite automata, and these are the basic attributes of the architecture of this deterministic finite automata. So making use this, try to construct some deterministic finite automata. So our finite automata we can also call it as a deterministic finite automata. The type of finite automata we see with the output, that is a DFA, NFA and epsilon NFA, right? So the now I am going to be interchangeable that word. When calling finite automata, you can also call it deterministic finite automata at this discussion, right? So the continuation of this, let we construct a deterministic finite automata to accept the string 0, 1, 1, right? 0, 1, 1. So for this we have an attribute called m is equal to q comma sigma delta comma q comma f, right? So the capital Q, the big Q is represents the number of states in a state diagram. So sigma is the number of inputs. What are those inputs will be represented in that state diagram. Delta is a transition function, that is a Q into sigma. The Q into sigma, that is the number of transition we'll get, that is up to Q. And Q is a small q is a start state, F is a final state, right? So having understood these 5 tuples, so try to construct a deterministic finite automata to accept a string that is 0 1 1 or 0 0 1 1 1, right? So let me consider that the 0 initial state is a q1, so that arrow mark indicates the start, that is start. And that the input is in this case input is a sigma, that is sigma is equal to 0 comma 1, right? So from this string you can understand sigma is equal to 0 comma 1. So that are the inputs. So input when the input 0, it will remain in the same state. So when the input delta comma, that is a transition can be possible. So q1 comma 0, the q1 is a current state, 0 is a input, right? So when you are inputting for this when you state diagram at the state q1, then the what is the output state or next state is a q1, we will be remain in the same state, right? So you will be remain in the same state. So the next other possible input is a 1, right? Because from the bank we can say sigma is equal to 0 comma 1, so 0 or 1, so 0 is over here, now can give 1. So when 1 is input, then it goes to the next state called q2, right? The next state q2. So this it indicates with a double circle, it seems to be final state or accepting state, right? So we can have the input 1 at q2, it will remain in the same state. So input 0, then it will go to the next state that called q3. So from q3 can give 0 comma 1, it will be come back to the q2. So let me discuss in the subsequent stage, that is, so at the time you can understand the architecture of the 5 tuples involved in the state deterministic finite automata and state diagram for this example called 0 1 1, right? So what are the states involved here? So you can spell one by one those 5 tuples. So q is equal to big Q is equal to, Q is what? That is a finite number of states involved in the state diagram, right? So q1, q2, q3, 3 states are involved in this diagram. So what is the input? Input is a sigma is equal to 0 comma 1, 0 or 1, right? So next we have transition. So the state start state is a q1. So final state is equal to f is equal to q2, that is the final state. So transition function, that is a delta is equal to q big Q into sigma. So the Cartesian product of those possibilities will be there. So start state is q1 and final state is q2, right? So from this diagram I hope you will be able to follow, that is the state diagram for this string to accept 0 1 1 or 0 0 1 1, right? So these are the 5 tuples. You can after once we reach the q2, that is the accepting state, that is a final state. Even if you going beyond that, then there is some waste will be there, that will put it to the dead state. So q3 is a dead state here in this case, right? So we can have we are observed this problem, that is a state diagram. So now we can see the complete record we can record in a transition table. So transition table is a what is a transition table? So what are the inputs? Inputs are 0 comma 1, that is a sigma. And what are the states are there? q1, q2, q3. So let's see that q1 comma 0 means q1 is a current state and input is 0, and where it will go? It will go to it will remain in the same state, that is called q1. So that we can record in a transition table. The q1 comma 0, the delta of q1 comma 0, that is q1, right? So next we have q1 comma 1. So q1 comma 1, it go to the q2, right? What is the delta of q1 comma 1 is equal to q2, that is q2 means the current state is q1, the input is 1, and it will go to the next state called q2. In the previous case, that is 0, so it was remain in the same state. Similarly, you can have the other transition. So q2 comma 0, it is a q3. So then q2 comma 1 is a q2 itself, right? Remain in the same state. So next q3 comma 0 is a q2, q3 comma 0 is q2, and q3 comma 1 is also q2. So I hope from this explanation we have followed that what is a state diagram and transition table. So these are the major milestones in the while constructing the deterministic finite automata for any strings you are going to be accept, or any language you are going to be accept for the machine, right? So let me consider one more the elaborative examples we have experienced in our daily life. So we have understood from our elders and parents. So the human life how will be followed, that is. So the start with this. I am going to be given same the example which will resembles the deterministic finite automata. So the life will be start when after birth, right? After birth. So after birth there is a nursing is required. So when you have enough nursing or the suitable nursing, then we may reach the childhood, right? So childhood may be at the age of 4, 5, 6, right? So after nursing, childhood will be there, and after childhood, then we have we have enough food, and you have a play and entertainment or exercise. Then we will reach the teenage, right? So teenage. So teenage, after the teenage, maybe we may going to be complete the high school education or maybe college education. Then we will get the further specialization or professional courses, the education. Then we may reach the adult age. Then when you go to the adult age, then you will get enough education. Then you may go for the service. So when you go for the service, then you will get you will start earning. When the start earning, then you will build a life. Then so long that you will be earned that, then one fine day we may reach the old age, right? So the old age may be required medicine, or maybe some service we are rendering, right? So there could be a possibility of the completion of life, that is maybe death, right? So this kind of flow you might be experienced, or we may be heard from our seniors or parents. So this may be one example which will be resembles your deterministic finite automata. So let me see, if the old age, if you don't get in medicine, we may going to be expire, right? So maybe at the adult age you may not you may get an accident, or maybe you may not get suitable medicine facility, or maybe pandemic diseases, and due to that may go to the death stage, right? And also at the teenage also, they similarly maybe do not have any facility, or some disturbance, or no medicines. In that case also death may be there. Maybe childhood also, there may be accident, no medicine. There may be possibilities of disturbance from the several diseases, or there could be several difficulties are there in the life. Due to that maybe some chronic disease will be there. So due to that no medicines are there, and will go to the death state, right? So similarly we can have at immediately birth there is a disease, maybe accident, or maybe no medical proper medical facility. That could be possible. That from this diagram you may be able to appreciate the deterministic finite automata concept, which may be quite resembles our human lives from the birth till death. So similarly, you can going to try to construct a deterministic finite automata which accept the input 1 1, right, or the input symbol set 1, right? Here input is a 1. So how to construct that finite automata for to accept the string 1 1? So start with the Q0. Let me start with the Q0, and give an input. Then it go to the Q1, right? Next state, and give one more input. Then it go to the Q2. And we have a third input called 1, then it go to the Q3. So we need to be decide it should be extract the string that is our final state. So that will be indicated with the Q3, then we can finish it up. So this will be a machine will going to be accept the string the 1 1 1, right? So similarly you can go to have a one more that machine should be accept all strings having exactly 1A, right? Exactly 1A. So exactly 1A, how can construct that is a start with the Q0, right? So give an input A, maybe in this case sigma is equal to A, the input symbol are A. In the previous case sigma is equal to 1, that is the input symbol is 1, right? So we can have the input symbol A comma B. So we can enhance our library, that is input symbol is A comma B. So then A is the input, then it go to the next state Q1, and when B is input, it will remain in the same state, right? Remain in the same state. So we can have that is a when Q1 is a B, when you are in the Q1 and the input is B, then it will remain in the same state. So it is when from Q1 and A is the input, then it will go to Q2. Q2 is a dead state. Q2 is a dead state. So all strings having exactly one A, right? When is Q2 and the B is the input, then it will remain in the same state. So that we have to accept the exactly one A, right? So the one more example, all strings having at least one A. So at least one A. Similarly, you can start with the initial state called Q0 and input A and input B. It will be remain in the same state, and when input A, it will go to the Q1 and B, it will be remain in the same state. So all string having at least one A string can accept from this machine, right? So we can have an example of sixth example. So all strings having at most one A. So at most one A means either 0A or 1A or no A. So instead of saying 0A, then you can say no A or 1A, right? So let's begin with the Q0. The inputs are here. I should say that is a or B. I said 0 or 1. Here the input is A. That is the input A is means 0, and input B is means 1. Input B is means 1, right? So input B, that is at most 1A means 0 A, right? At most 1A means 0A, right? So when you have B, that is indicates that is a B is a 1 here. B is a 1 here. When is B, and it will remain in the same state. When is A, it is A 0, it will go to the Q2, that is a dead state. So AB, it will remain in the same state. So can at most 1A can be accept. So either 0A or 1A or 2A or 3A, so on, that is, right? So at most 1A is a initial state and the final state. Both are initial state is also final state. So final state is a final state. So Q2 is a dead state. So coming to the next problem, design finite automata which accept only those strings which are start with a 0 and end with a 1 over the input symbols are 0, 1. So let's start with the Q0. Start with the Q0. So the what is the input? 0, and it will go to the Q1. At Q1 there is a 0 input will remain, and the one input will go to the Q2. One input will go to the Q3. So I should wrongly mention that is actually Q2. So even if we call it Q3, no problem. Our that big Q will become Q0, Q1, Q3. 3 states are there. So we can have that is a all Q0, Q1, Q2. So Q2 will be indicated here. So 0, 1. So delta of Q1, not is a Q1, Q0, Q1, okay, Q1, 0 is equal to Q1. So delta of Q1, 1 is equal to Q2, that is actually Q3. That is Q3. So delta of Q2 is equal to 0, that is a Q2. Wherever Q2 is there, we please refer that is a Q3. So Q3, right? So Q3. So the strings you can accept 0, 1 or 0, 0, 1, 0, 1 or 0, this 0 and 1 is the final state, and 0 and this is 1 and this is 1. So or 0, this 0 and this is 1 and this is 1, or 0, many number of zeros, 1 and many number of 1s. So this inside strings will be enveloped with a 0, beginning 0 and lastly with a 1. So this machine will going to be accept the following strings called 01, 001, 011, 0011, right? So the one modification, instead of calling Q3, call it as Q2, that right, Q2. So going to be design one more which checks the given binary number is even, right? Binary number is even, right? So example 0 G 0110, so this is a even number, right? So 110, this is a odd number, right? Odd number. So we can have, that is a for this we can construct a transition diagram. So start with the Q0 and go to the Q1 with a 0 input, and we can have next the 0 input here at the Q1 will remain in the same state, and give a 1, then we will go to the Q2, right? So give to the Q2, and at Q2 we input a 0, then we will go to Q1, right? So the at the beginning Q0 the input is 0, we went to Q1, then when input is 1 you should go to the Q2, right? So this diagram, at Q2 1 will be there, we remain in the same state, right? So after constructing this diagram we can have a transition table for this. So delta of Q0 comma 0 is a Q1, delta of Q0 comma 1 is equal to Q2, right? So similarly, so Q1, delta of Q1 is a final state, so the delta of Q1 is equal to 0, it will remain in the same state, and 1 will go to the Q2. Similarly Q2 is 0, it will go to the Q1, 0 it should go to the Q1, right? So this is wrong, that is Q2. And when you have okay, this is interchange, that is interchange. So when it is 0 it will go to the Q1, and when it is 1 it will be remain in the Q2. So these two values should be interchanged, that is. So that's modification. So we can test the example when the input is 0110, right? 0110, you can check whether this number is even or not. So when you have 0, so 0 input, so we can have the 0 input will go to the Q1, and when we have 01 will be accepted now, then the next input will be 1, then it will go to the Q2, right? So when the Q2 0 1 will be accepted, so next we can give an input called 0, then it will go to the Q1. So 0110 will be accepted, and finally it reached the final state. Means it is accepted that stage, means that given number is even. Let me check the one more example, that is a 0111, 111, right? 0111, so that is 01 Q11, 01 Q11, and 01 Q21, and we have at Q2 there is input 1, then will be 011 Q2 will be remain same state, it not reach the final state. When it not reach the final state, it in other words we can say it not accepted the string. It not accepted the string means that is it is not a even number. So that is what's good for this design. So the one more important aspects of that, the machines will be accept the empty language or empty stage, right? So construct the DFA for this. So Q0 is a initial state, and it assume that there is a input symbols called A and B. So when A is given, it will remain in the same state. Even if B is given input, then it will remain in the same state. So then we can say that is a empty language. The language which is accepted by the tested by the machine, that is a empty stage. No input will be, the language is empty. So we can have the other side, we have the example, we can have a Q0, and it will be indicated with the double circle. It is a final state and initial state as well, and A is and input and B is input. So it can accept any string or no string. It can accept any string or no strings. So that will be a all strings will be accepted. For example, there is a empty string and there is a epsilon null string, and maybe AB or AB or AB or AB many times. So that is all strings will be accepted. So we can have empty strings. We have Q0. Q0 is there, initial state and final state. Then the input is a comma B, and it will go to the Q0. It go to the Q0, and it will be A comma B. So A comma B. So we have that is a this is a empty or epsilon. Sorry, this is epsilon. can also, some textbook will refer as lambda. So language of the empty string, that is a language of the empty string, that is one more example, design a deterministic finite to accept all strings with the prefix AB. So normally we can have 5 tuples will be represented. So the number of states will be participating, and the number of inputs A comma B, and those transition m delta into q, q into sigma. So that is a delta will be we have seen in the previous example. So try to construct the machine which will able to accept a string which is always having a prefix AB, right? So then A is a input, then go to the next state called Q1, and B is input, and go to the next state called Q2, then it will be accept, that is. So any strings, all strings with a prefix AB, all strings may be beginning 0, no strings, and you will now, if you no string, then it will accept the AB, right? So accept the AB, and if you have a string that is a AB, when is input, it will go to the Q1. When input B, then it will go to the Q3. When it go to Q3 at Q1 there is a input B that go to the Q2, and the other input called A, that is go to the Q3, that is called a dead state. When we have two input called A comma B, it will remain in the same state. So the, for example, AB, that is a prefix with the AB means no strings are there, only AB, and we have a prefix with the AB. So prefix AB and string AB is there, and prefix AB, then several ABs are there. So like that, n number of ABs you can have, and all those strings will be always ended with coming out with the prefix AB, right? So we can have one more example, all binary strings containing substrings 001, all binary strings containing 001. For example, you can have the blank 0 0 0 0 0 1, right? So substring containing a substring called 001, substring called 001, right? So inputs are 0 comma 1. So sigma is equal to q into sigma, that is So we can have a start with an initial state. So I may be named with the q0. So I just empty, that is it understood it have some name. So we have 0, then it will go to the next state. When it is 1, it is coming back to the same initial state, that is a beginning state. And at here from 0 you can give 0 input, then you go to the 0 0. So 0 0, and we have a 0, then it will go to the remain in the same state, and when we have 1, it will go to the 0 0 state, right? So when input called 0 comma 1, it will be remain, that is. So here we can have assume that is a 0 0 1, right? 0 0 1. So all string substring will be 0 0 1. So here the stop string will be 0 0 1. So another example you can have. So we can take 1 0 0 0 and 1, right? So substring is 0 0 1. Here the one string, the string 1 is a main string, maybe complete maybe a string, but substring is 0 0 1. So take one more example. So 2 times 1 here, and the 0 and the 0, and we can have 1 here. Similarly 0 0, we can 0 1, this 0, and we can have several number of zeros you want to take it, and finally 0 1 1 will be completion. So similarly like that, several strings you can test it, that is. So this will be going to be complete with help of the what is called 0 0 1. So we can have one more example, that is to accept a substring that is AA or BB, right? AA or BB. So we have start with the Q0, and go to the, when an input is there, then it go to, when input A is there, it will go to the Q1, right? So when the from the Q1, when the input is there, it will go to the Q3. So AA, the string AA will be accepted, right? So if you want to AA, then AB, here AB will be there. So that also you can construct. So let's complete this diagram. So when A is the input, it will go to Q3, when B is the input, it will go to the Q2, right? When B is the input, it will go to Q2, that is a dead state, right? So that is a dead state. From the Q2 it will go to the Q3, and we can have when the Q0 A is input, that it went to Q1, but now Q0 is the input B, then it will go to the Q2, right? So we can construct A or you can come via this B. So you can end with the substring is B, will be assuming that obtaining, right? From this side via Q2 you are coming, you will get BB. Via Q1 you are coming, you will get AA. Anyhow, it winds up at Q3 since it is a final state. So that is one example. So we can have some more interesting examples. So construct a DFA to accept a odd number of B's, right? Odd number of B's. So odd number of B's means we have an initial state and give an input called B, and it will go to the second state. So second state is a odd number of B's. Odd number of means 1, 3, 5, so on, that is. So here one B is accepted, then we finish it up, right? We close it up and declare it as acceptable. So the other B input you are going, it will coming back to the same state, right? So we can B, that is for one iteration it is a B, and second iteration B, 3 B's will be there, so 5 B's will be there. Like that, all number of B's will be going to be accepted by this machine. So second example, even number of A's, right? Even number of A's means the beginning state and final state will be same. So the even means 0, 2, 4, so on, that is, right? So the even number of A's, A will be 1, and go to the fourth state, and it will be coming back to the third state. So at the given instant of time, if you remain in the same state called 3, then the 0 A's. If you go one cycle, then you will get a 2 A's. Second cycle 4 A's. So third cycle 6 A's. So on, that is even number of A's will be going to be accept, that is, right? So coming to the 15th problem, that is a even number of A's and odd number of B's, right? So even number of A's and odd number of B's. So even number of A's we have. So you can start state 1 and second state, the second state is 2, then the input is given A, then it will go to the next state called 2. When the here we can give because the even number of A's, right? So even number of A's, so 1 A is over and 1 B is over, odd B is over. So we get the fourth state, then we can give one more input called A, then it will go to the final state, right? Why I am saying final state? So even number of A's, there is a 1 A and second A, the 2 A's are there, 1 B is there. So odd even number of A's and odd number of B's will be obtained. So the third state will be a final state. So the remaining diagram we can complete, that is. So when input A at input third state, it will go to the 4, and it will B, it will go to the second. When you give A, it will go to the first state. The other side you can come from the state 1 to the final state. So input B, then it will go to the final state called 3, right? So in the reverse also, when you input the B at the third state, it go to the beginning state. So this diagram will able to accept, state diagram will going to be accept the strings even number of A's and odd number of B's. Similarly, the other problem you can see even number of A's and even number of B's. From this problem you are able to understand, so you can easily construct the even number of A's and even number of B's acceptable machine. So that strings will be the 1B and 2A 1B and so on, that is a example of 15th problem, that is a even number of A's and odd number of B's. Anyhow, come to the 16th problem. So start with the initial state called state 1. When given input and go to the second state, get given input will go to the third state, so the fourth state. So fourth state become final, because the question is here even number of A's and even number of B's, right? So one one even number of A's and even number of B's, that is. So that we have to change it, that is odd number of A's and odd number of B's, that is actually. So this title we have to change it, odd number of A's and odd number of B's. So here the diagram, the state diagram designed for odd number of A's and odd number of B's. So here we have 1A and 1B. So 1A and 1B will be there, and either side you can coming one from this side also you come maybe 1b and 1b 1a. So that is a odd number of a's and odd number of this problem. This state diagram suitable for odd number of a's and odd number of b's. So if you want to construct a even number of a's and even number of b's, so then we need to make that is a diagram the what is called the states to become final state. So here AB, 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 right? AB, AB. So the we have a construct the DFA to accept at least 3A's and 3B's, but in any order. So in that case we have AA, 3A's are there, right? So we have to attach another 3B's, 3B's are there. So after 3A, then 3B's will be attached and reach the final state, right? But the condition is, but in any order we can perform that design that constructed DFA. So coming to the BB, right? So this BB can connect with the AA of this vertical and horizontal lines. So the finally going to be constructed, you can say that AA BB. So we can come A and BB, and you can also BB AA. From this side you can come BB AA, we will get that is. And other examples also you can have BAA. So you can give from here BAA and BB, right? So the other example BBAA. So on that. So we can have the lastly BA. So BA you can have that any order you can follow that state diagram will be accepting that. Design a DFA to accept strings A's and B's whose length are multiples of 4, right? So earlier one 3, now it is a multiples of 4, right? So we can have AB, then we have the next state will go, and we have input will go to the next state, and we have input will go to the next state. So we will come back, that is right. So there is a 4 paths are there, so 4 states will be involved, so that form a multiples of A, that is. So after understanding some of the problems from the deterministic current automata, so we may be more interested the improvement or improved version of this. So here we can what will be upon that digital machine will be have the number of inputs are limited, so the finiteness will be there. So because in the nature or in the real life example may not show, they are flooding the results, flooding the inputs or outputs. So in order to catch out them, so we need to be try to collect all those, or we have to try to accommodate in our computer, for which DFA may not alone sufficient. So for this in order to accommodate the huge inputs and outputs, for which we need a non-deterministic automata, because that sigma into q we have seen in the previous example, sigma into q, that is a the number of transition functions will be up to q. Now it is a 2 power q, because the inputs are and outputs are more. Not to accommodate them, we need to be consider more inputs and outputs, for which there is a little make space for the more inputs and outputs. That can be possible with a non-deterministic current automata. So the previous example we have seen that how to construct the deterministic current automata, and those notations we have followed. So examples also we have seen, that is for every string x there is a unique path from initial state to final state, right? So that is a path from initial state to reachable final state. X is accepted if and only if this path is ends to at a final state. So that is a deterministic finite automata. For non-deterministic finite automata, for any string x there may be a exist none or more than one path from initial state to the final state, right? So there is a one minimum one path will be there. Here there is a 0 path or more than one path may be possible, that we can call the non-deterministic finite automata. So I am going to discuss in detail about non-deterministic finite automata in the subsequent discussion. So right now I am going to elaborate this. So to construct a non-deterministic finite automata, to accept the strings called 0 1 1. So q1 0, it go to the q2 1, and it will go to the 0, and q4 will be remain in the same state for the input. So from q3 we can also have 0 1 0 0 we can have, that is q5 to q6. so the q1 q2 q1 q2 q3 q4 q5 q6 will be there. For that corresponding transition table will be there. So I will going to discuss in detail in the subsequent discussion. The one more improvement over that, the NFA, that is a epsilon NFA. Epsilon NFA is a we can have, that is a the q into sigma is up to 2 power q. Now sigma q into sigma union with the epsilon, right? So that why epsilon will be there. Even no input, that will going to be a transitions. So that transitions we are going to be see in further in a subsequent discussion, that is the epsilon NFA Deterministic finite automata. So the one such example here we can glance, that is start q0 a and no input, that is epsilon go to the q1, and input b remain the same state, and epsilon, there is a no input, that is epsilon is there, it go to the q state, q2, that is a final state, right? So this one such examples you can right now we can observe, that is, so that is the epsilon closure function. That epsilon closure function is a reachable function. So reachable, that is epsilon closure is a q0 is equal to q0 comma q1 q2. so the q1 q0 to q1 reachable. So epsilon q1 to q2 reachable, that is a q2 to q2 reachable. We will be discuss in detail in the subsequent discussion. So the one more topic called regular expression. So far we have seen the seen that strings or language, right? So those strings we can express with help of the regular expression, right? So given a regular expression, how to obtain a deterministic finite automata? Because we have seen several examples of deterministic finite automata. So now we can going to be see that how to construct a deterministic finite automata for the given regular expression. So consider the regular expression called 0 0 bracket 0 plus 1 whole star, means 0 plus 1 is a repetitive string, star is a the 0 or 1 or 2, any number of times can be repeated that. So for that example you can have 0 is input, and it go to the next state called p, right? So the next input is there 0, because this 0 is there, and we have reached the final state called 0 plus 1, right? 0 plus 1, here is 0 and is 1. So 0 0 0 plus 1. So 0 plus 1 whole star, 0 plus 1 star can be have many number of times, right? So this is a equivalent deterministic finite automata for the given regular expression, right? So let me see this in a more detailed form. S is a 0, and the next state will be p, and next state will be 0, then it will go to the q, and q can have, so from S also we can have, that is a null string, right? So that is a dead state. So from S and p, q in input will go to the dead state, and 0 when will remain in the same state. So we can have q1 will be 0, that is q0, q1 will be a final state. So here we can have 0 0 1. So 0 0 0 1 0 0 0 1. So I need to be mentioned here 0 1 0 comma 1. So 0 0 0 1. So anyhow this is a dead state. So go to the one more example. Design a deterministic finite automata to accept a string 0 plus 1 whole star 1 1, right? So here 0 plus 1, that is a 0 plus yes, it is a initial state 0 plus 1 means 0, and parallel it will be happen many times, it can happen, that is why star, right? So there is a 1, and the q0 will be final state. So this we can elaborate further, that is, so 0 1, and it will go to the p state. So 0 it will remain in same state, 1 will go to the sp state. So 1 will be there, it will go to the spq state. So spq state, so spq is the final state, and it will be a 1 1, right? So 1 1. So 0 1 0 plus 1, so 1 1. So we can have that. So 0 it will be coming from the initial state, and it will be how that is. So one more example, you can have design a DFA to accept a regular expression 0 0 0 plus 1 star 1 1, right? So 0 0, and we can have what is called p, right? P is the next state. So we have dead state called phi, that is when you give 1 it will go to the 1 state, from the p you can go to 1 state. So you can proceed 0 0, they are given in a string, right? Regular expression. So you can have q, right? So we can have 0 plus 1, and 0 plus 1 will be there, and we can have qr we have 1 1, right? so can have PQRT, so that is a final state, so can have 0 and this is 0 1, it will be there, so 0 0 1 1, right, or 0 0 is a first string, 0 plus 1, 0 plus 1 will be a middle string whole star, we can have from this we can have many times, that is, and finally 1 and 1 we can have, that is. So the constructed DFA to machine consider the accept the empty strings, so that is a empty strings we have seen in the beginning example. So more elaborated the constructed the language that DFA will be accept the zero strings. So here we have no final state, so since no final state, it will be wound up, that is. So I hope you followed the concept called deterministic finite automata and conversion of regular expressions to the deterministic finite automata. So the little definition about finite deterministic non-deterministic finite automata and epsilon non-deterministic finite automata, that going to be discussed in detail in the subsequent discussion. So I thank you for your patient listening and interest shown on deterministic finite automata and its allied concept. So if you have any queries, you please post the queries to this mail ID. Thank you.